Hello, this is Jack Jackson. We're going to look at a couple of things in this video. First, we're going to start with looking at this little animation that Tim Brzezinski put together. It's pretty cool in GeoGebra. So here we have a circle. Right now it's radius 5. I can control the size of the radius there, but let's make it as big as possible so we can see it well. And we have this diameter that's a distance across here. And what we're going to do is we're going to take that red length and stretch it around the circle. So there's one full diameter wrapped around the circle. And the second one, how many of these diameters are we going to be able to get wrapped around the circle? That's the big question. And if you look, we get 3 full diameters and we get some leftover part. That leftover part turns out to be about 14% of a diameter. Okay. And actually, the number of diameters that you get is this number that we call pi. It's the same. It doesn't matter whether the circle is bigger or smaller. Let's reset and watch it again. If you're looking at the number of diameters, it's the same. One full diameter, second full diameter there, a third full diameter, and about 14% of another diameter. So once again, it doesn't matter if it's a small circle or a big circle. If you take the circumference of the circle, the distance all the way around, and divide it by the distance straight across through the center, the diameter, divide the circumference by the diameter, you get a same number every time. It's a little bigger than 3, around 3.14. But it turns out to be a same number every time. We call this number pi. So pi is defined to be the diameter of a circle, circumference of a circle divided by its diameter. And that turns out to be a number that is an irrational number. Okay? So pi is the circumference of a circle is the arc length found by going all the way around the circle. We divide the circumference c of the circle by its diameter d. We obtain the same constant regardless of the size of the diameter of the circle. We call this constant pi. So we define pi to be the circumference divided by the diameter. Pi is defined to be c over d. It turns out pi is a little bit bigger than 3. To the limits of, say, a TI-84 calculator, it's about 3.14159.265. But people have worked out the number of digits of pi to many, many, many digits. So I had a student recently, Molly Kingston Kelly, who worked out this poster. She did a big history of pi. So shout out to Molly for this poster that she put together. And here are many, many, many digits of pi, 3.14159 and so forth. Da, 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 da. It goes all the way across here, and it keeps going here, and it keeps going all the way here. And and then there's more down here, way out here. And this history of pi, the ancient Babylonians had it to at least one decimal place, approximated as pi, or 3.1. Okay, a little bit later, one found 3.125, which was accurate at least to one decimal place. Archimedes made a huge advance. He was the first one to give an approximation between two numbers. He's probably the first one to realize that this is actually an irrational number. It's not just a really nice fraction of integers. And he did it by taking n-gons and circumscribed them, a 96 gon circumscribed and inscribed, and got bounds for it, for the area of the circle between the areas of those two figures, and from that he was able to deduce bounds on pi. He got it to between approximately 3.1408 and 3.1429, somewhere in there. So his approximation is in there. Brahmagupta Archimedes was in Syracuse, on the island of Sicily. He's a Greek culture mathematician. Brahmagupta, about 640 of the Common Era. Archimedes was about 250 BCE. Brahmagupta conjectured that it approached the square root of 10, which is not true, but it's an approximation. Zhuangzi, 480 in China. He gave an approximation. He basically used the same method Archimedes did, but went one step further to 192 gon. doubling the sides there. Madhava in India was the first person to use an infinite power series to approximate pi, and was able to use it to approximate pi correct to 13 decimal places. Sir Isaac Newton, one of the inventors of calculus in 1665, was the first person to use the integrals to approximate, and he's in this vicinity here, 15 decimal places. Thomas Vantet Delange in 1719 used Gregory's arctangent series to approximate it to 112 places, doing a lot of tedious computations by hand. He was able to get it out this far, so now we're getting out pretty far. Euler popularized the symbol pi, so that's the first time we really start using the symbol pi for it. Of course, the concept had been around a lot earlier. And he roughly proved that his transcendental, this proof wasn't complete, but he wrote that it popularized this symbol from his books. In fact, Euler is responsible for lots of our current notations. Lambert, Johann Lambert, in 1768 was the first one to prove that pi is irrational. Now, an irrational number is a number that cannot be expressed as a ratio of two integers. Okay, and it cannot be then it cannot be a repeating or terminating decimal. So we know at this point around 1768 we knew for sure that it was irrational. George Buffon in 1777 related pi to a new way to approximate it using some statistics. Lindemann in 1882 proved that pi is transcendental. An algebraic expression or algebraic number is a number that can be found by built up out of abstract multiply, divide, powers, roots, and so forth. Transcendental numbers cannot be done that way, so it's sort of a step beyond irrational. Ramanujan, very, very famous and brilliant Indian mathematician, discovered infinite series for many things. He felt like he had divine inspiration for that, and he was able to use that. Now, on this last line down here, we're getting to the starting to use some technology. D.F. Ferguson in 1946 was the first person to use a calculator to approximate pi. He got 528 digits of pi. Galion and Boyer in 1973 computed over 1 million digits using a mainframe supercomputer. Took about 22 hours and 11 minutes to get 1 million digits. Contrast that with something that's coming up here in a second. David and Greg Shudnovsky in 1989 were brothers that developed an infinite series that rapidly converges to pi. And so pretty much all the algorithms since then have been using their algorithm or some slight variation of it. Kondo and Yi in 2011 computed over 10 trillion digits using the Shudnovsky algorithm. Okay. And then the current record holder is Emma Awao. She set the current record for the most computed digits of pi. She computed over 100 trillion digits, a lot more than fit on this paper, in just over 158 days using the Y-Cruncher and system that Yi came up with. And that comes out to over 73 million digits per second. So if you think back here, think about how the computing power changed. 1 million digits here took 22 hours. Over here is 73 million digits per second. So much that's the growth of better methods, but then also the computer technology growing. So better and better approximations of pi came along. A better understanding of pi throughout the ages came along when we understood that this was we understood as a constant way back in the ancient times, but getting a better idea of the size of that constant and the fact that it is an irrational constant came along. So interesting thing there. Now next we're going to talk a little bit about some fundamental circle theorems. So here's another GeoGebra activity. Let's look at this one here and see if you can see what's going on here. So we've got a circle here, and we're looking at this. So first of all, see what we've got. We've got a chord. So see a chord to the circle. And we're drawing a perpendicular to that from the center of the circle. See that? Now we have another chord here, and we're drawing a perpendicular there. So those are right angles. Next, we want those distances to be the same. See that? What does that say about the two chords? Well, you can see the two chords are the same. And this actually is an if and only if. If you start with the two chords being congruent, you can get these distances the same. If you start with the distances the same, you can get the chords congruent. So it's an interesting little basic result. Now, I'm going to let you prove that yourself. Okay. And so here's the proposition here, actually a couple of, about four propositions here that are similar. This one says they're all related to the same picture that we just looked at. You can a segment joining the center of a circle to a point on the chord bisects the chord if and only if the segment is perpendicular to the chord. In the plane of a circle, the perpendicular bisector of a chord contains the center of the circle. The distance from the center of a circle or sphere to a chord is the distance between the center and the line containing the chord. And for a circle or for two circles of equal radii, the two chords are equidistant from the center or centers, if and only if the two chords are congruent. So see if you can prove these four things, and I'll give you a hint. This one just boils down to finding some congruent triangles somewhere. So see if you can mess with this a little bit, come up with some congruent triangles and prove these results. Okay, let's look at this one. Given a line that's in a plane of a circle and contains the outer endpoint of a radial segment, the line is tangent to the circle if and only if it's perpendicular to the radial segment. And for each part of the circle, there's exactly one tangent line to the circle at that point. So let's investigate that just a bit. So I'm going to go to a new GeoGebra thing and just build the whole thing right here in real time. So here's a circle. We pick a point on the circle. And the idea is we want to take a radial line segment that's from the center point to the point on the circle. This can go anywhere we want around the circle. Right? This one draws the size of the circle. Let's kind of get it in the center of the screen here. Now, if we draw a perpendicular line to this line through that point, notice that it's going to be tangent to the circle, and it's an if and only if. So this is a quick way to get a tangent line to a circle. Now, why is that true? Well, why is that going to be tangent to the circle? Well, let's remember that the perpendicular distance is the shortest distance. So let's start with the tangent line and show that it has to be perpendicular. Well, if it's not perpendicular, there's going to be some place out here where it is. So suppose this one is perpendicular. Well, that means this point is closer to the center than this point, which means this has to be inside and the circle in the interior, and that's not allowed because we said this was tangent. Okay, so if we go the other direction, suppose we start with it being perpendicular. Why is it tangent? Well, once again, if you get a point here, this point, all these points here have to be further away than this point because this is a right angle, which that's the closest distance. We've looked at that concept before, I think. So interesting thing to notice there about tangent lines and radial segments. Okay, so there's only going to be one tangent line for every point there because there's only one perpendicular for every point. So that gives us some nice little preliminary results about circles. We started with some definitions of circles. We talked a little bit about pi. We talked a little bit about some basic theorems that come from finding some congruent triangles. So there might be some different things that you might be able to prove about circles with some congruent triangles. Remember, one thing, of course, we have is that these radial segments are all congruent. So that gives you some congruent line segments that you can work with to maybe get to where you can have some congruent triangles in certain situations. If you can do that, then you may be able to prove the things you're looking for. So kind of keep those things in mind when starting with some more basic results about circles.